For centuries, humanity looked up at the night sky and saw a predictable clockwork machine. Everything just made sense. But right at the dawn of the 20th century, one man completely shattered that illusion. Welcome to this explainer, where we're going to dive into exactly how Albert Einstein rewired our entire understanding of space, time, light, and energy.
You know, when we hear the name Einstein today, we instantly picture the wild hair and the universally revered genius, right? But long before that, he was just this incredibly curious kid, literally mesmerized by the invisible magnetic forces pulling a simple pocket compass. Fast forward to 1905, though, and that curious boy had grown into a practically invisible 26-year-old technical assistant. He was a third-class examiner, completely isolated at the Swiss Patent Office in Bern, basically because he couldn't even land a university teaching job. He didn't even have easy access to scientific reference books. So you have to ask yourself, how on earth did this completely unknown outsider manage to rewrite the fundamental laws of the universe?
To really get inside his head, we kind of have to look at his family's history. Einstein's dad and his uncle Jakob ran an electrical engineering firm in Munich. They built dynamos and power plants. Young Albert showed a ton of technical aptitude early on, so the plan was always for him to take over the family business. But the firm eventually went bankrupt after losing some major contracts, and a second attempt to rebuild the business in Italy totally flopped too. Watching his father age prematurely under that crushing stress of debt gave Albert this lifelong deep aversion to commercial, profit-driven pursuits. As he famously put it, the thought of expending his inventive power for the dreary oppression by capital was just unbearable. So it drove him inward. It pushed him into a life of deep intellectual solitude where his imagination could roam completely free.
Section 1, 1905, The Miracle Year. 4 papers that changed physics.
Okay, let's dive right into this. That intellectual solitude at the patent office absolutely set the stage for what we now call his annus mirabilis, his miraculous year. And honestly, this is arguably the greatest scientific underdog victory in history. Working pretty much alone, using his free time during office hours to scribble down equations, Einstein published 4 papers in the journal Annalen der Physik that literally changed the face of physics forever. I mean, just look at the sheer timeline of this output. In March of 1905, he explained the photoelectric effect, introducing the revolutionary concept of energy quanta. Then, in May, he published a paper on Brownian motion that finally gave the scientific community the empirical proof they needed to accept that atoms actually exist. Wild, right? Then, in June, he drops the special theory of relativity, fundamentally linking space and time. And as if that wasn't enough, he follows it up in September with the principle of mass-energy equivalence, giving us the famous E equals mc squared. 4 massive pillars of modern physics, all built in a single year, discussed mainly with a tiny circle of friends, like his patent office buddy Michel Besso, who Einstein lovingly called the best sounding board in all of Europe.
Section 2, Atoms and Light. Demystifying the photoelectric effect.
Let's zoom in on that first major breakthrough of 1905. Because despite all his later fame for relativity, it was actually his work on the photoelectric effect that won him the Nobel Prize in Physics in 1921. At the time, everyone strictly understood light as a continuous wave, but Einstein realized that under certain conditions, the math just didn't add up. So he proposed that light could also travel in discrete, finite little packets of energy. To really grasp the problem he was solving, we first need to define something called the work function. In physics, the photoelectric effect happens when light hits a metal surface and actually knocks electrons right off of it. But those electrons, they're holding on tight. The work function is the strict minimum amount of energy required to rip an electron away from that specific metal. If the light hitting the metal doesn't meet this exact energy threshold, what we call the threshold frequency, absolutely nothing happens. 0 electrons are emitted. And this brilliantly illustrates how Einstein's energy quanta actually behave. Think of it like a toll booth on a highway. The car approaching, that's a photon, a tiny, massless particle of light. The money the driver is carrying is the photon's energy level, which depends entirely on its frequency. The toll booth itself is the metal surface, and successfully paying and passing through represents an electron getting knocked free. Now here is the absolute genius part. It doesn't matter how intense the light is. You could have a blindingly bright light, which is the equivalent of a massive traffic jam of thousands of cars, but if none of those drivers have enough money to pay the toll, nobody gets through. On the flip side, a really dim light with a high frequency is like just a couple of cars pulling up, but their pockets are completely stuffed with cash. They pay the toll instantly and boom, electrons are emitted. This proved once and for all that light wasn't just a wave, it operated as discrete particles too. Section 3. Bending Spacetime. Reimagining Gravity. So he'd conquered the microscopic quantum world, but he obviously didn't stop there. By 1916, Einstein had shifted his sights to the macroscopic universe. He wanted to figure out gravity. Ever since Isaac Newton, gravity had been seen as this mysterious pulling force that acted instantly across vast distances. Einstein thought, well, that's incomplete, which prompted him to completely reimagine the very fabric of reality itself. To wrap our heads around this, we have to contrast his two theories of relativity. Now, there's a super common misconception out there that special relativity only deals with constant velocity and can't mathematically handle acceleration. Actually, scratch that. It's simply not true. Special relativity can handle accelerated frames of reference perfectly well. The real difference, practically speaking, is curvature. Special relativity operates in a flat space, what physicists call Minkowski spacetime. General relativity, which came out a decade later, bridges the gap by introducing gravity not as some invisible pulling force, but as the actual physical curvature of spacetime. It's fundamentally built on the equivalence principle, which basically says you cannot uniquely separate gravitation from inertia.
So the crucial point here is that spacetime is not just some empty container. It's not a rigid, fixed stage where the cosmic drama of planets and stars just happens to take place. With general relativity, the stage itself becomes an active character in the play. Massive objects, like our sun, physically warp and curve the space and time around them. And it's that curvature that dictates how everything else moves. Space and time literally have no separate existence outside of the gravitational field.
Section 4. Einstein's Modern Legacy. Powering Today's Technology.
Now, at this point, you might be wondering, okay, this is incredibly profound, but it's also kind of abstract. Bending spacetime? Quantum write packets? It sounds like stuff that only belongs on a university chalkboard. So, why does this matter to us today? How do physics papers written over a century ago by a patent clerk using a pen and paper actively power your modern everyday life? Well, the truth is, they absolutely do. We are literally surrounded by Einstein's legacy every single day.
Let's take a look at how this all builds into our reality with 3 incredible examples. First up, solar power. The massive solar arrays powering the International Space Station, or even just the solar panels on your neighbor's roof, rely entirely on the photoelectric effect. They use semiconductor materials like silicon to capture photons and knock electrons loose, creating an electric current. Second, think about the GPS navigation in your smartphone. Satellites in orbit actually experience time slightly differently than we do down here on the ground because of their high speeds, yep, that's special relativity, and because of Earth's curved gravitational field, that's general relativity. If engineers didn't program your GPS to actively account for Einstein's theories, your maps would be miles off target within a single day. And third, even something as simple as the barcode scanner at your local grocery store operates using technologies fundamentally rooted in his discovery of light quanta.
From that miraculous burst of creativity in 1905 to his later years in America at the Institute for Advanced Study in Princeton, Einstein's life was defined by this beautiful, persistent curiosity. After his legacy was secure, he spent his final decades in relative intellectual solitude once again. He was striving against the grain of the larger physics community, desperately trying to find a unified field theory, a single, elegant mathematical framework that would tie all the forces of nature together. He never quite found it, but he never stopped looking up, and he never ever stopped questioning the fabric of the universe. Which brings us to our final thought. Science is never truly finished, you know? It's an ongoing conversation with the cosmos. Albert Einstein showed us that you don't need a massive laboratory or the immediate approval of the academic establishment to change the world. You just need a willing mind, a notebook, and the courage to look at a beam of light or the ticking of a clock and ask, why? So if a 26-year-old clerk could completely redefine reality from a tiny desk in Switzerland, what incredible mysteries of the universe are still out there right now, just waiting for someone like you to uncover? Thanks for joining me on this explainer. Keep asking questions.